So equivalence relations are sort of a way that we have to say that things are in some facet, some sense, some aspect, they're the same. So we're going to get into the specific definition of it and do some sort of intuitive examples, but the thing that I want to impress upon you as we start this new topic is that in mathematics, you can have things that aren't technically identically the same thing, okay? They're not equal, but they're the same for all we care. For whatever mathematical interest we have in it, they're the same. You know, an example of this would be something like, you know, in geometry class, you can have two triangles that are completely different triangles, like their locations in the plane, they're in different locations, right? Maybe they're rotated relative to one another. But you could say those two triangles are congruent. And if all you care about is geometry or geometric properties, two congruent triangles are kind of the same, right? So that's the kind of sense of sameness that we're going for here, something like geometric congruence. And when you get into higher and higher math classes, this idea of equivalence relation rears its head quite a lot. So like when you're taking a class called abstract algebra, there's a certain kind of structure that we study in those kinds of classes called groups. There's also things called rings and fields. And we have a word to mean when two groups or two rings or two fields are essentially the same according to their algebraic properties. They may not be literally exactly the same in terms of like one of these things might be a set of matrices and the other one might be a set of numbers. So they're not technically the same objects that we're talking about, but when you look at their algebraic properties, they're the same. When that sort of thing happens, we say that those things are isomorphic. And when we're in the land of topology, you know, geometric, it's kind of like you can think of it as like geometry where things are a bit stretchy. Then we can talk about things being the same for all we care. And we call those things homeomorphic. So there's all kinds of words that we use to indicate things are the same in some sense that we care about. And almost always these senses, that when we have this sense of sameness, it's an example of what we call an equivalence relation. So here are the algebraic properties that we need to have to define an equivalence relation. We've got these three properties. The first one is the reflexive property, the second one's the symmetric property, and the third one's the transitive property. So let's go through these three properties one by one. But before talking about the specifics of those, I just want to point out that an equivalence relation on a set is just a relation on the set that has those three properties that we were talking about. So when we're doing equivalence relations, our equivalence relation is on a set A. So we're no longer doing, for this section, we're not doing the relations from one set to a different set. We're only doing relations from a set to that very same set. So if the name of the set is A, we're talking about relations on a set A. So a relation on a set A is said to be reflexive. That just means that for every little a in big A is related to itself. So reflexivity means every element is related to itself. The second property, the symmetric property, so our relation R on the set A is symmetric if for every A and B in the set, if you know A is related to B, then it must be the case that B is related to A. So symmetry means anytime you have like an A comma B in the relation, then you also have B comma A. The easiest way to say this one is A related to B implies B is related to A. Okay, and then transitivity is for any, so you got this universal quantifier again, for any A, B, and C. If you know A is related to B and B in turn is related to C, then you get this transitivity property that A is related to C. So this one is A related to B and B related to C tells you A is related to C. And like I said, any relation that has all three of these properties is called an equivalence relation and will be sort of what we think of as sort of a generalization of equality. It's sort of like equals in some sense. We use this symbol whenever we're referring to some general abstract equivalence relation. We'll use the symbol tilde to refer to it. But when we have specific ones, we may use a different symbol. But that's just our generic symbol for an equivalence relation. Okay, so let's take a look at this toy example here at the bottom. We got the set A is 1, 2, 3, and then we got this relation S defined on A. And I want to know, is it reflexive? Is it symmetric? Is it transitive? And then if you answer those 3 questions, you'd know whether or not it was an equivalence relation. Let's take a look. So first, let's ask about reflexivity. Is it the case that every element in A is related to itself in S? So remember, whenever you see 1, 1, that means 1s1, right? 1 is related to 1. When you see 2 related to 2 here, you got 2s2. And here you've got 3s3. So I can see, yes, it's the case that every element is related to itself. S is reflexive, since 1 is related to 1, 2 is related to 2, and 3 is related to 3. Okay, how about the symmetric property? Is it always the case that anytime you see A is related to B, then the reverse is also true? So just check each ordered pair in the relation. So I see 1, 1's there. If I reverse 1, 1, I still get 1, 1. So it's obviously the reverse of 1, 1 is there. Same holds true for 2, 2, and 3, 3. For 1, 2, if I reverse that, I get 2, 1, and then I do see that 2, 1 is there also. So here's 1, 2, and then there's the reverse of it. And for 2, 1, its reverse is there also. For 2, 3, its reverse is 3, 2. So that's there, and vice versa. So I can see S is symmetric. Okay, how about transitivity? So transitivity is that property that if you see A is related to B, and then that B is related to a C, you need to also have A is related to C. Okay, so I want to see if there's any way I can violate that. So let's pick on this ordered pair 1, 2, and then 2, 3. So here I see 1 pairs with 2, and then 2 in turn pairs with 3. So if it were to have the transitive property, I would need to see 1 gets paired with 3. But I don't have 1 paired with 3 in this relationship. So S is not symmetric. S is not transitive because 1 is related to 2 and 2 is related to 3, but it's not the case. Kind of looks like a dollar sign, but it's not. It's not the case that 1 is related to 3. Okay, let's consider a really familiar example of less than or equal. Is less than or equal reflexive? Is it true that x is less than or equal to x for every x in the real numbers? Sure, because it's less than or equal. X is less than or equal to x, right? So it is reflexive, yes. Is it true that x being less than or equal to y implies y is less than or equal to x for symmetry? Well, of course not. 1 is less than or equal to 2 does not imply 2 is less than or equal to 1. So it's not symmetric. And then is it true that if x is less than or equal to y and y is less than or equal to z, does that imply that x is less than or equal to z? You betcha. This is just, if you put these things on a number line, you see that it's clearly true. So just a little reflection on less than or equal. So we see that less than or equal is not an equivalence relation because it fails to have the symmetric property. So in the previous example, we saw an example that had reflexivity and symmetry, but not transitivity. And here's one that has reflexivity and transitivity, but not symmetry. And of course, you can come up with relations that have whatever combination of the properties that you want, okay? But I certainly was not expecting less than or equal to be an equivalence relation because we don't use less than or equal as a way to tell things are the same. We always use less than or equal as a way to distinguish things as being not equal, right? It does allow equality, but in general, the concept of it is it's a comparison to like contrast things, to talk about when one thing is greater than the other. Okay, how about set containment on P of A? Remember, that's the power set. Remember, the power set is the set of all subsets of A, and A is this particular set 1, 2. So let's write down what those sets are. So power set of A would be all the subsets of the set containing 1 and 2. So I'd have the empty set, I'd have the 2 singletons, and then I'd have the whole set. So there's the power set of A. And I can compare the sets within there with containment, set containment. So how about reflexivity? Do we have reflexivity? Is each one of those sets contained in itself? Yes. Every set is contained in itself. Is it symmetric? If one set's contained in the other, is the reverse also true? Well, no. It's not symmetric because, for example, the singleton 1, well, we can do it with the empty set. The empty set is contained in 1, but the singleton 1 is not contained in the empty set because the empty set doesn't have any elements. So it's definitely not symmetric. And how about transitivity? Well, yeah, that's a general property of set containment. If A is contained in B and B is contained in C, then A is contained in C. That was one of the properties that was in the list of set properties. So this is another example like the previous one that had reflexivity and transitivity, didn't have symmetry. Here's the example that I alluded to a bit earlier. If A, the set that we're thinking about comparing things in, is the set of all triangles in the plane, and then the thing that we're using to compare triangles is geometric congruence, this is an example of an equivalence relation. It's reflexive because every triangle is congruent to itself, of course. Remember back in high school geometry class, you had like the side theorem for telling if two triangles were congruent. It didn't have anything to do with how the triangle was oriented or what order you did these things in. If two triangles have all their sides, if corresponding sides equal, then they're congruent, right? So we can just use side to prove everything that I'm talking about here. So we certainly have reflexivity, symmetry. If you had, one triangle was congruent to, like one triangle A is congruent to another triangle B, then it's certainly true that all their sides are in proportion, so it doesn't, or all their sides are equal and correspondingly, so it doesn't make any difference what order you talk about that in. And then same with transitivity. If triangle A is congruent to triangle B, then you got side there, and triangle B is congruent to triangle C, you got side again, then triangle A would be congruent to triangle C. So there's an example of an equivalence relation. Okay, so now we're going to do something a little bit more technical. We're going to prove that congruence modulo n, where n is greater than or equal to 2, is an equivalence relation. Just as a reminder, let me remind you what the definition of modular congruence is. A is congruent modulo n to B if n divides B minus A. So this is our definition of modular congruence. And I want to prove that that relationship is, in fact, an equivalence relation. I guess I should specify what set it's an equivalence relation on. So in the original problem here, let me specify that it's an equivalence relation on the integers. All right, so let's prove it. So we must prove, if we're going to prove something's an equivalence relation, we must prove that it's reflexive, transitive, and symmetric. So let's just break that proof into the 3 parts. So reflexivity. To prove reflexivity, remember what we got to prove is that for every A in the set, in this case the set is Z, we want to show A is related to A, is what we got to show. That's our goal. For every A in the integers, A is congruent to A modulo n. So if I want to prove that, I'm going to take an arbitrary element in the integers and prove that this is true about that. So the proof will start off like this. Let's let little a be an integer. And what I want to argue eventually is that A is congruent modulo n to A. But if I think about backing up one step from the target, I know that according to the definition above, that I need to show that n divides A minus A. But I know that A minus A is equal to 0, so what I really want to show is n divides 0, right? So I'm trying to, sometimes it's helpful to sort of work backwards from your target to think about, so that you'll know when you're done, or you'll reach an intermediate point that lead you to the n. Here's what I'm going to do to get to that target. So I want to show that n divides 0. I know that n divides 0 because a minus a equals 0 equals n times 0. And I'm going to point out that 0 is an integer. I'm going to erase the target stuff here now. So since I know a minus a equals n times 0, where 0 is an integer, I can see that n divides a minus a. So hopefully that's clear. I've got a minus a is n times 0. That's exactly what it means to say n divides a minus a, because I've expressed a minus a as n times an integer. Thus, a is congruent modulo n to a. Now, this proof that I'm giving you here is sort of a template for how all reflexivity proofs go. I want you to notice where I started and where I ended. Every reflexivity proof starts with an arbitrary element in the set, and then you show that it's related to itself. Okay, let's do symmetry next. Okay, to prove symmetry, let me remind you of the symmetry property. It's a universally quantified statement here for all a and b in the set. If a is related to b, then b is related to a. So because it's universally quantified, I have to start with 2 arbitrary elements in my set, and then I got to prove this hypothetical, or this conditional statement that has an if part. So I'm going to take 2 arbitrary elements and then assume the if part is true. So assume a and b are in my set, and assume a is related to b. So this, in our particular context here, would be something like this. I would say, well, let's let little a and little b be 2 arbitrary elements of the integers, and I want to suppose the if part is true, so I want to suppose a is congruent modulo n to b. And what I want to eventually argue is that b is congruent modulo n to a. So I want to be able to turn that relation around. Well, I don't think this will be too challenging. Since a is congruent mod n to b, we have n divides a minus b according to our definition. That in turn tells me that a minus b is equal to n times k for some integer k. Now check it out. If I reverse the order, if I do b minus a, that tells me b minus a is equal to n times negative k. And I know negative k is an integer because k was an integer. So this in turn tells me that because I've taken b minus a and expressed it as a multiple of n, that says n divides b minus a. And if n divides b minus a, that's exactly what it means to say b is congruent modulo n to a. So now let's look at our template again. I'm big on templates in this class. I started with 2 arbitrary elements. I suppose they're related in one order, and then I showed that they're related in the other order. That's your template. Okay, let's do transitivity. Okay, so here, going back to the definition on the previous page, we have a universally quantified statement. Involves 3 universally quantified variables, and then the hypothesis is a is related to b and b is related to c. That's what we assume is true, and then that's what we have to argue is true, is a is related to c. So I'm going to take 3 arbitrary integers, a, b, and c, and then suppose a is congruent to b mod n and b is congruent to c mod n. And then I'm going to argue a is congruent to c mod n. All right, so setting up the proof here, it'd be let a, b, and c be integers, and suppose a is congruent mod n to b, and b is congruent modulo n to c. A being congruent to b mod n implies n divides b minus, or a minus b, and b being congruent to c mod n tells me that n divides b minus c. Thus, there exists some integers, let's say k and l, such that, well, a minus b can be written as n times k. So that's just taking advantage of this statement. If n divides a minus b, that's the same as saying a minus b is a multiple of n. And similarly, b minus c can be written as n times that other integer that I picked, l. So n divides c minus b, that's just using the definition of divides there. All right, so now check it out. I'm going to focus on these two equations. I'm just going to add them together. Notice that the b's will cancel out. So what we're going to end up with here is a minus c. Notice that's the same as a minus b plus b minus c. Just those b's cancel. But then that's the same as n times k plus n times l, which is n times k plus l. And k plus l is an integer. So that grand finale tells me that n divides a minus c. So a is congruent mod n to c. And that is the proof. I want you to notice the template for what's going on here. Started with a is congruent to b and b is congruent to c, and arrived at a is congruent to c. This is one of those proofs, I think, you will want to dissect and thoroughly understand because it's such a good exemplar for how you do proofs of reflexivity, transitivity, and symmetry. In other words, proving something is an equivalence relation. And if you can master this proof, I think you can do just about any kind of equivalence relation proof. So this is a good one. So I'll give you a chance to practice your skills a little bit here on the concept of equivalence relations. The first example is sort of one of those toy examples where I've given you just some set, A, B, C, D, and some randomly generated relation. And I want you to think about which properties, reflexivity, symmetry, and transitive, this relation possesses. And so if it is reflexive, I want you to be able to tell me why. If it's not, also be able to say why, that sort of thing. And then on the second example here, I've got a relation, E, defined on the integers, defined according to this relationship here. A is related to B if A plus B is even. And I want you to prove that that is, in fact, an equivalence relation. So that previous proof that we just did about modular congruence would serve as a really nice model for how you would do number 2 here. So hit pause and do these problems. And when you come back, we'll run through it together. All right, welcome back. Let's have a look here at number 1. So the question is it reflexive? You've got 4 elements that you have to check. Are they all related to themselves? So I need to have little a is related to little b is related to little b, little c is related to little c, and little d is related to little d. In terms of ordered pairs, I need to see a, b, b, c, c, d, d. Do I have all those ordered pairs? Let's just go down the line and check. Well, there's a, there's b, b, there's c, c, and there's d, d. So yes, R is reflexive since for every x in big A, x, x is in the relation a, b, b, c, c, and d, d are all in R. Okay, so how about the property of symmetry? Is it always true that, for every 2 elements, A and B, let's say, if A is related to B, is it also true that B is related to A? I don't think so, because in particular, like I'm looking at, well, here's A, B. Do you see B, A anywhere else in there? I don't see B, A, so it's not symmetric. So A, B is in R, but B, A is not in R. So that's it. There's a counterexample. And then how about transitivity? Is it always the case if, like, you have some A is related to B and a B is related to C, that you get A is related to C? I don't know. I just have to go through and look. I see A is related to B. Do I see a B related to something else? Well, there's B related to C. Do I have A, C? Yeah, there it is. There's A is related to B, and then B is related to D. Do I have an A, D? Yeah, okay, so I got that. Okay, how about A is related to C? Okay, and then C in turn is related to D. So I have A, D, so that works. A and D, that won't really do. Okay, how about doing something where B is the first component? B is paired with C. C is in turn paired with D, so I have B, D. B is paired with D. And okay, so this one looks like it actually is transitive. So yeah, so I'm just checking all the possibilities basically. It's actually a little bit of a pain to try to write up a proof with these toy examples of transitivity, because you have to establish that for every possible way that you have like an A comma B and a B comma C, that you have an A comma D. But I sort of did it by inspection. I sort of just went down the line, and so we verified by inspection that whenever X comma Y is in R and Y comma X is in R, or I'm sorry, Y comma Z is in R, then X comma Z is in R. To make a full accounting of that, you'd have to sort of make a table or something like this, and this may be something that you need to do. Like you could do something like, okay, how would you organize this into some sort of tabular form? All pairs of the form A comma B and B comma C, and then you'd ask yourself, is A comma C in R? And so like I'd have to make a table like where I said, well, okay, I've got, like there's some trivial ones like this, A comma A and A comma A are in there. And then it's true that A comma A is there. So there's ones like that. And then you got ones like A comma B is in there, and then B comma C is in there, and then you've got A comma C is in there, and you got ones like A comma D was in there, and, or I'm sorry, A comma C was in there. And then in turn, C comma D was in there. And then you also found that A comma D was in there, yes. So anyway, the point is that you could make an exhaustive list of this sort of thing and check all the possibilities, okay? All right, let's have a look at the second problem on this skills check. So this one was a proof problem. You need to prove that this relation E, defined by A is related to B if and only if A plus B is even. We want to show that that's an equivalence relation. So we're going to break this into three parts. We'll do the reflexivity. All right, so remember the template is you have to take an arbitrary element in the set in question, and that, in this case, the set on which the relation is defined is Z, and we want to show that A is related to itself. So we want to show A, E, A, like that. A is related to A. But that would mean A plus A is even. But that means the same thing as 2 times A is even, right? Well, clearly that's true. If you start, sometimes it's helpful to sort of think in reverse. So my proof's going to go like this. Observe that A plus A equals 2 times A. And let's point out A is an integer again. So A plus A is even, because we've expressed A plus A as 2 times an integer. That's the definition of even, right? Thus, that's the definition. If the sum of two numbers is even, those two numbers are related, right? So thus, A is related to A. So we write that this way, A, capital E, A. Okay, how about the symmetry part? So we have to take two arbitrary elements this time, and we're trying to prove this conditional. If A is related to B, then B is related to A. So we assume the if part is true. So we suppose A is related to B. And our goal is to prove that B is related to A. But this is going to be pretty straightforward. A plus B is equal to B plus A, right? We know that addition is commutative. So we know A plus B is even, but A plus B equals B plus A. That's just a known property of integers. So B plus A is even also. And hence, because B plus A is even, that's what it means to say B is related to A. So we started off with A is related to B, and we arrived at B is related to A. All right, transitivity. So here we have to take 3 arbitrary elements in the set on which the relation is defined, and we need to suppose 2 things. A is related to B and B is related to C. So that tells me that A plus B and B plus C are even. So that tells me that A plus B can be expressed as 2 times an integer, and likewise B plus C can be expressed as 2 times an integer. And parenthetically over here, I'm going to just point out that K and L are integers, of course. And, something that jumps out at me to try here is just to add the two equations together. So if I add these equations, just add their left sides and add their right sides. I suppose you could do some substitution game too, but this comes down to, we get A plus 2B plus C equals 2K plus 2L. And from there, we can subtract 2B from both sides, and we get A plus C is equal to 2K plus 2L minus 2B, which I can factor a 2 out of. And notice that what we factored a 2 out of, what was left was an integer. So the K plus the L minus the B is an integer, because K, L, and B are all integers. And so when you add and subtract integers together, you get back integers. So that tells me that A plus C is even. And I finally can conclude then that A is related to C, which we denote by A, capital E, C. All right, so check it out. We did what we're supposed to do. There was our hypothesis. A is related to B, and B in turn is related to C. And then we arrived at A is related to C. All right, and there's our proof. The next topic I want to talk about is equivalence classes. So conceptually, the idea of an equivalence class isn't too big of a deal. So let's suppose that tilde is an equivalence relation on A. And you start with some element, X, in the set. And what you do is you gather up all of the elements that are equivalent to X under this relation tilde. And you call that the equivalence class of X. And so here's the technical definition of it, but you'll see that it's just what I said. So X bar is all those things in A that are equivalent to X. There's another common notation for equivalence classes, X with the brackets around it. But I'm probably going to stick with the X bar notation in this class. I just wanted you to be aware of that. And also, whenever you have an equivalence relation, you have a bunch of different equivalence classes potentially for that relation. If you group all those distinct equivalence classes together and form a set out of it, we call that set A mod tilde. So this set right here is often called A mod tilde. And we also call it the quotient. This is a topic that's really important when you get into higher level math. Quotient spaces are a big object of study in abstract algebra and topology and just about any kind of modern mathematics. Like I said, though, the idea of an equivalence class is that X bar is just all those elements in A that are equivalent to X. So let's see how this works with a small example. Here I've got A is the set of integers 5 through 12, and we're defining an equivalence relation on that set A by saying A is equivalent to B if A and B have the same remainder when you divide by 2. Now, if you think about that, two elements will have the same remainder when you divide by 2 if they're either both even or they're both odd, right? There's only two possible remainders when you divide by 2. A remainder of 0, that's when something is even, or a remainder of 1, that's when something is odd. So really, this is just another way of saying two things are equivalent if they have the same parity. They're both even or they're both odd. Now that we understand how the equivalence relation works, let's write down what those equivalence classes are. By the way, you should verify for yourself that this is indeed an equivalence relation. So it wouldn't be a bad idea for you to pause the video here and just check the 3 conditions of an equivalence relation. It's reflexive, it's symmetric, it's transitive. But assuming that it is indeed true that this is an equivalence relation. Let's write down what the different equivalence classes for tilde are. So let's just start with an arbitrary element of the set. I'm going to just start with 5 because it's the smallest element in the set. And I'm going to look at 5 bar, the equivalence class of 5. So what are all the elements in A that are equivalent to 5? Well, that would be all of the elements that have the same remainder when you divide by 2. Now, when you divide 5 by 2, you get a remainder of 1 because it's odd. So 5 bar is just going to consist of all the other odd elements in A along with 5 itself. So 5, 7, 9, and 11. And also, notice that if I would take any individual element in this equivalence class, let's say 7, and look at its equivalence class, I'm going to get exactly the same equivalence class. This is the same as 7 bar. 7 bar are all the things that have the same remainder when you divide by 2. That's what you get with 7. So 7's remainder is 1 when you divide by 2, and these are all the elements that have the remainder of 1. So likewise, this is the same as 9 bar, and it's the same as 11 bar. Now let's look at an element that we haven't considered yet. So we've done all the odds, so let's look at 6 bar. So 6 bar would be all those things that have the same remainder as 6 when you divide by 2. So now we're talking about all the evens. So we'd get 6, 8, 10, and 12. And for the same reasons as before, if I would take any element in this equivalence class and look at its equivalence class, I would get exactly the same equivalence class. The reason for this basically boils down to the properties of an equivalence relation. In particular, transitivity and symmetry will guarantee that if you take any element in an equivalence class and look at that element's equivalence class, you're going to get back that very same equivalence class that you chose that element from in the first place. So this is the same as 8 bar, 10 bar, and 12 bar. And so then, what is the quotient? What is A mod tilde? That's just the collection of all of the distinct equivalence classes. And so that would be 5 bar and 6 bar. One thing I would like to point out, just as an observation, it turns out it's a general fact, but I just want to point it out now just as an observation about this particular quotient. So notice the distinct equivalence classes are disjoint. If you think about that, it kind of makes sense. If you had 2 equivalence classes that had any kind of overlap, there would be an element that was equivalent, having that common element that would be equivalent to both of the things that you took the equivalence class of. Using transitivity and symmetry, you would be able to argue that all of the elements in both of those equivalence classes would have to be equivalent to one another. So in fact, if there's any overlap between 2 equivalence classes, they have to actually be the same equivalence class. So distinct equivalence classes must be disjoint. And also notice that the union of the equivalence classes is all of A. We'll address these 2 observations formally in a theorem before too long, but I just want you to notice that it's true about this particular example. If you take the union of the elements in 5 bar and 6 bar, you get back all of A. And 5 bar and 6 bar are completely disjoint from one another. One of them consists of odd numbers and the other one consists of even numbers, so they're disjoint. Okay, let's look at another equivalence class. This one's a bit more substantial than the previous one. So this time we're looking at equivalence modulo 5 on the whole set of integers. So now we've got an infinite set on which we're looking at an equivalence relation. And I want to find all of the distinct equivalence classes if we can. Well, let's just jump in. And now Z is an infinite set, so where do you start? Well, let's just start at 0 and look at the equivalence of class of that and see what we end up with. And then we'll maybe move to the next integer that's not already spoken for, and so on until we have decided that, hey, we've accounted for all of the integers. Let's start with 0 bar. So 0 bar, these are the set of elements in Z having the property that x is congruent modulo 5 to 0. So if we think about that, what does that mean? So just as a reminder, if we say x is equivalent modulo 5 to 0, that means the same thing as 5 divides x minus 0. Of course, I'm not really going to write x minus 0 because that's silly. It just means 5 divides x. So if I want to look at all of the integers x satisfying 5 divides x, I'm just looking at multiples of 5 here, right? So if I would just list out the elements of this set, I would get ... negative 15, negative 10, negative 5, 0, 5, 10, 15, and so on. Okay, so at this point, in the whole set of integers, we've accounted for all the multiples of 5. So now let's look at a number that we haven't accounted for in the previous equivalence class. So notice, by the way, if I would do negative 5 bar, I would get the same set. If I would do 15 bar, if I would take any of the elements in this set and put a bar on top of it, I would get back that same equivalence class. So there's no need to consider 5 bar or 10 bar or any of those other ones in that set with a bar on top. Okay, so let's look now at 1 bar. We haven't accounted for 1 yet. So what is 1 bar? These are the set of integers with the property that x is congruent mod 5 to 1. Well, if you think about it, any integer that is congruent to 1 modulo 5, that just means that it has a remainder of 1 when you divide by 5. Because x being congruent mod 5 to 1 is the same as saying 5 divides x minus 1, which is the same as saying x minus 1 equals 5 times an integer, which is the same as saying x is 5 times an integer plus 1. And if you think about the division algorithm, if I've written x in this form, it tells me that k is the quotient and 1 is the remainder. So any integer x that is congruent to 1 mod 5 has a remainder of 1. So all I need to do to write down this equivalence class is write down all the integers that have a remainder of 1 when you divide by 5. And so if you just take all the multiples of 5 and add 1, you're going to get those numbers that have a remainder of 1. So I'd get negative 14, negative 9, negative 4, positive 1, positive 6, positive 11, positive 16, and so on. And then exactly that same logic would apply if I move to the next number that's not accounted for. Maybe I can look at 2. So 2 bar. These are going to be the elements that have a remainder of 2. And listing them out, I get this. I'm just adding 1 to the previous set, essentially, so that I get remainders of 2. And then I can look at the ones where I have a remainder of 3. So now that we know the connection to remainders, we know that the only possible remainders are 0, 1, 2, 3, and 4, because your remainder always has to be non-negative but less than the number that you're dividing by. So we're going to get a 3 bar, and we're going to get 4 bar. But there's no need to write 5 bar because, as we pointed out earlier, 5 is an element of that first equivalence class. And so if I would look at the equivalence class of 5, I would just get back the same thing as the equivalence class of 0. And so it's pretty clear now that we've exhausted all of our possible equivalence classes. Let me go ahead and list the elements of these last 2. At this point, I think you can see that what we've done is every integer at this point is spoken for, because every integer has a remainder of 0, 1, 2, 3, or 4 when you divide by 5. So all of the elements of the entire set Z are spoken for at this point, and so I'm done. I've listed all of the different equivalence classes. So at this point, we have discovered that Z mod equivalence, Z mod congruence modulo 5, this quotient is the set 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. In fact, the common notation, this particular quotient space is really important. Typically, it's just referred to this way, Z mod n, or I guess maybe it's more like this, Z n, just a sort of a simpler notation for that same set. This is a very important quotient space that gets used quite a lot, especially in the land of number theory. And it's closely related to the idea of residues that we talked about back in the basic number theory chapter. The distinct equivalence classes are represented by exactly the remainders, right? And when you do residues, that's what residues are. Residues are the remainder when you divide by n, where n is the modulus under consideration. Let's do one more example of finding the equivalence classes and therefore the quotient space of an equivalence relation. This one's kind of a crazy one. So we're defining an equivalence relation tilde on R2, the plane. So the elements that we're going to be relating to one another are ordered pairs in the plane. And the definition of the relation is that an ordered pair AB is equivalent to an ordered pair CD if and only if this relationship holds between the components of those ordered pairs. So the sum of the squares of their components must be equal in order for them to be equivalent. And we want to see if we can think about what the equivalence classes would be. We've got a whole plane full of points to think about. So let's just start picking some, let me draw a picture of the plane just so we have a visual here. So in order to do an equivalence class, you have to pick a particular element and then look at the equivalence class of that element. So maybe I'll start just right here at the origin, 0, 0. Let's look at 0, 0 bar. What would be equivalent to 0, 0? Well, let's write down so according to the definition of the idea of equivalence class, this would be the set of all A comma B in R2, because that's the set on which we're defining our equivalence relation. And then AB needs to be equivalent to 0, 0. But this is the same thing as saying A squared plus B squared equals 0 squared plus 0 squared, which is just 0. Well, which ordered pairs in the plane satisfy A squared plus B squared equals 0? Well, since A squared is always, A squared and B squared are both non-negative, the only way that this can give you zeros if both A and B are 0. If either A or B was non-zero, that sum of the squares would be strictly positive. So this just consists of the one point, 0, 0. 0, 0 is the only A comma B that can satisfy that equation. So interesting, this equivalence class only contains one single element. Well, let's pick a different element now. Maybe I'll just kind of work along the x-axis, Let me pick, let's see, this is 1, 2, 3, 4. I'm just trying to get a sense of what's going on. So let me pick this point. So here I'm doing 1, 0. I started with 0, 0. Let's look at 1, 0 and see if we can figure out what's going on with its equivalence class. So 1, 0 bar is the set of all A comma B in R2 having the property that A comma B is equivalent to 1, 0. And then we think about what the equivalence relation, like what does that mean? So we have to go with this equation up here, and applying that, this becomes the set of all AB in the plane, where A squared plus B squared equals 1 squared plus 0 squared. Of course, I'm just going to write that as 1. Well, hey, I recognize this. This is a relation that we've actually talked about previously. The set of all AB that satisfied this equation is exactly a unit circle centered at the origin. So that equivalence class, if I would draw it over here, it looks like, so this green circle here is 1, 0 bar. And I bet you can see where this is going to go. But let's check a few other examples before we sort of make up our mind what's going on. How about 2, 0 bar? Well, just like before, this will be the set of all points in the plane with the property that AB is equivalent to 2, 0. So that would mean A squared plus B squared needs to equal 2 squared plus 0 squared. So that's 4. And hopefully you recognize that this equation defines a circle of radius 2 centered at the origin. And so 2, 0 bar is another circle centered at the origin, except this time it's like a little bit bigger. Excuse my lumpy looking circle, but pretend that's a perfect circle there. So there's 2, 0 bar. And I think you can see now that basically any point that you would pick on the x-axis, the equivalence class is going to be a circle centered at the origin through that point on the x-axis. So if I did one at 3, 0, I would get a circle that has radius 3. If I do one at 4, 0, I get a circle of radius 4. But I also get those circles at in-between points. So like 2.5, I would get a circle of radius 2.5. At pi, I would have a circle of radius pi. So, if I did, here's pi, then I would get a circle of radius pi out here, right? So this would be pi 0 bar, and so on. So how do we describe all these different equivalence classes? R2, that's the space on which our equivalence relation is defined. If I look at this quotient, the set of all equivalence classes, one way that I could describe it, it's going to be the set of all circles centered at 0, 0. And there's also, we did get one equivalence class that was not technically a circle. It was a degenerate circle. So we did have one equivalence class that was just a point, the origin itself. But if I look at all of the circles centered at the origin, along with the origin itself, that forms my quotient. And one thing I want you to notice again is that all of the equivalence classes are disjoint from one another. Every one of those circles, those concentric circles that are centered at the origin, if you pick any two distinct circles like that, they're disjoint from one another because they have different radii. So all of the equivalence classes are disjoint from one another. And if you union up all of those circles, it forms the whole plane, along with the origin. You have to add in the origin too. The same phenomenon was happening in the previous example. If we took all those equivalence classes when we were doing congruence modulo 5, and we union them together, we get all of the integers. And also we see that each one of these equivalence classes are disjoint from one another, because the first one are the integers that have remainder 0 when you divide by 5, and the second one's where you have remainder 1. And so they're all disjoint. So just like the first example, we're seeing that the equivalence classes are disjoint from, so distinct equivalence classes are disjoint from one another. And the union of all the equivalence classes, in other words, the union of all the elements in the quotient space, forms the underlying set. Let's take a few minutes to do a skills check here. So for the first problem, I want you to find all of the distinct equivalence classes for congruence modulo 3. So this will be very similar to our congruence modulo 5 problem. And then the next one, we have an equivalence relation defined on all the reals, defined by A is equivalent to B if the absolute value of A and B are equal. So I want you to check that tilde is an equivalence relation, part 1 or part A. And then secondly, I want you to describe all of the distinct equivalence classes for tilde on R. And I want you to think about the relationship. Are those equivalence classes disjoint from one another? And is their union forming all of R? So go ahead and press pause, and we'll work these together when we come back. All right, welcome back. If you thought about the example we did for congruence modulo 5, we noticed that the equivalence class of an element was just the set of elements that had the same remainder. Now, since we're doing modulus of 3 here, our distinct possible remainders are 0, 1, and 2. And so that corresponds to exactly our equivalence classes. So we get 0 bar, which gives you just all the multiples of 3. Then you get 1 bar. Those are the elements that have a remainder of 1 when you divide by 3. And you'll get 2 bar, the elements that have a remainder of 2 when you divide by 3. And then our quotient space is Z mod equivalence mod 3, consists of those 3 equivalence classes, 0 bar, 1 bar, and 2 bar. Okay, for number 2, we want to first verify that tilde is an equivalence relation, and then secondly, we want to describe the distinct equivalence classes. So let's do that. So for part A, we'll check reflexivity. So to check reflexivity, we'll take an arbitrary element in the set. In this case, our set is all of R, so I'll take an arbitrary element X and R, and we'll simply observe that absolute value of X certainly equals absolute value of X. So X is equivalent to X, and we have reflexivity. Symmetry. So here we have to take 2 arbitrary elements in our set and suppose that they are related. then that tells us that absolute value of x equals absolute value of y. So absolute value of y is equal to absolute value of x because we know that equality has the symmetry property, and thus we end up with y is equivalent to x. So we started with x equivalent to y, we found out y is equivalent to x, and then we'll check transitivity. So here we have to take 3 arbitrary elements, x, y, and z, and then we suppose that x is equivalent to y and y is related to z, or y is equivalent to z. Then that tells us that absolute value of x equals absolute value of y, and absolute value of y is equal to absolute value of z. Well, equality is transitive, so since we have absolute value of x equals absolute value of y and absolute value of y equals absolute value of z, then we know absolute value of x, equals absolute value of z. Thus, x is equivalent to z. And we're done. Okay, so it was kind of a trivial thing that this was an equivalence relation, but it was a good exercise to go through the steps of it. But we certainly didn't have to do anything fancy to make any of those 3 arguments. We just needed to know the basic format for how you make the argument. So now let's think about the distinct equivalence classes. And I'll approach this a little bit experimentally. So the equivalence relation is x is equivalent to y if and only if absolute value of x equals absolute value of y. And this is defined on the reals, so I'm just going to think about numbers on the real number line here. Maybe we'll just start with 0. Like, what's 0 bar? Well, 0 bar would be the set of all x's having the property that x is equivalent to 0, which is the same thing as the set of x's with the property that absolute value of x equals absolute value of 0, which is just 0. There's only one real number that has an absolute value of 0, and that's 0. So 0 bar equals just the singleton 0. So let's maybe pick a different number on the number line. I'll just start, I'll do 1. I do realize, since we're talking about real numbers, that we have fractional values and weird irrational numbers to consider, but let me work with integers first just to get a sense of things. So 1 bar would be the real numbers with the property that x is equivalent to 1. So those are the real numbers with the property that absolute value of x equals the absolute value of 1, which is just 1. Well, which numbers on the number line have an absolute value of 1? Well, there's exactly 2, right? You'd get -1 and +1. And then I think I kind of see, at this point, I think that's enough to inform me about the whole number line. I think if I took an arbitrary, let's just say, like, if y isn't an element of R and y is not equal to 0, you can see that y bar is just going to be -y and +y. Because those are, if you take the absolute value of -y and +y, you get back y. The whole quotient space, R mod tilde here, is just going to be the set of all sets of the form -y, +y, where y is a real number. And that would even include the 0 bar. -0 and +0 would just collapse down to a single thing, to a singleton. So this is what all your equivalence classes look like. These, for the most part, you're getting these 2 element sets, except for the one degenerate case, 0 bar, you get just a single element. And again, if you think about it, each one of these distinct equivalence classes are disjoint, and when you union them all up, you get all of the real number line. So now I want to start talking about this property that I've been alluding to, this disjoint equivalence classes, and the fact that their union is the whole thing. So before we're doing that, we need to talk about partitions. So what is a partition? So a partition is just when you take a set and you chop it up into some disjoint pieces. Whenever you take an office space and you put partitioning walls into it, you're just dividing the office space up into distinct cubicles, right? To form the whole office. And the purpose of partitioning walls is to separate separate cubicles so that they don't overlap. People have their own space. Same sort of thing with the partition of a set. We just want to chop the set up into a number of pieces. Could be an infinite number of pieces. But the key thing is that those pieces that we've chopped it up into are separate from one another. They don't overlap. And the union of all these sets that we've chopped the big set up into should form the whole big set. And that's basically what the definition of partition is here in definition 3.40. So A is the set that we want to chop up into pieces, and the sets B alpha are the little chunks that we're going to chop A up into. These B alphas are a family of subsets of A, the pieces of A. And if it's going to be, so this is the thing that we're defining to be a partition, the collection of B alphas. So if that collection is going to be a partition, it has to have these three properties. First of all, we rule out that any of the pieces are empty, because it would be silly to have one of the sets in our partition be the empty set. That's not, not really, that would be sort of a degenerate thing to consider, right? So we're going to rule out the case that one of our partitioning sets is degenerate. The second thing is that if you look at any two of the sets in our collection of B alphas, they're either really the same thing or they're completely disjoint from one another. And then thirdly, when you union up all those partitioning sets, you should get back the whole set that those B alphas are subsets of. So if you have these three properties satisfied, you've got what's called a partition of the set A. So let's start with a really simple example. Here at the bottom, we have A, the set that we're going to partition are the integers 1 through 10. And then here's a collection of subsets of A. Now, if you wanted to, you could index this set, kind of like what we did in the definition there. So like that first set there could be B1, and the second one here could be B2, this one could be B3, and B4, and B5. Okay, so in this particular partition, we have 5 subsets of A, and I can see that all of those sets are non-empty. They all have at least one element in them. And then I need to examine, are those distinct sets disjoint from one another? Is there any overlap happening with them? Doesn't look like it. Like 1, 4, it doesn't overlap with any of the other sets. I don't see 1 or 4 in any of the other sets. 2, 3, 5, do you see 2, 3, or 5 in any of the other sets? No. Look at this set, 6. Do you see 6 in any of the other sets? No. 7, 8, 9. Do you see 7, 8, or 9 in any of the other sets? I don't. And then for the singleton 10, do you see 10 in any of the other sets? No. So the second property here is satisfied. So we already checked the first property. Each of those subsets is non-empty, and now we see that they're disjoint. Lastly, we need to make sure, if I union up all of these subsets in P, do I get back all of A, which is the integers 1 through 10? So let's just see. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9, there's 10. Okay, I see that all of the elements of A are accounted for in P. So if I union up P, I'm going to get back all of A. So here we see that P is in fact a partition. Okay, here's another example. We're still using A as the set of integers 1 through 10. And I've got another collection of subsets here. Like, so this could be my B1, this would be my B2, this would be my B3. Okay, this one only has 3. Okay, so the question is this a partition? Well, let's check the 3 properties of being a partition. Are each of those sets non-empty? Clearly they are, so the first property checks out. Are those sets disjoint from one another? Well, let's see. 1, the singleton 1, I don't see a 1 in any of those other sets. 2, 3, and 4. Do you see a 2, a 3, or a 4 in any of those other sets? Uh-oh, I do see. In fact, here's 3, and then here's 3 over here. So these two sets right here are not disjoint from one another. So this is not a partition. It fails property 2. So P is not a partition of A because property 2 fails. 2, 3, 4, and 3, 5, 6, 7, 8, 9, 10 are not disjoint and are not equal. It could be that you have the same set in the partition listed twice, but we know that that's just a redundancy that we can eliminate because we're talking about a set of sets, and anytime you talk about sets, you can eliminate redundancy. It does look like, though, that the third property of being a partition would have been satisfied because I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I did union up those sets, I would get back all of A. But it doesn't matter. It failed to be a partition because it failed one of the properties, property number 2. So now I'm ready to state the theorem that I've sort of been alluding to, and this is sort of a big deal theorem. It's called the Equivalence Class theorem. This is the theorem that says when you have an equivalence relation, the equivalence classes, in other words, the quotient space, forms a partition of your set. But it also says something else kind of interesting. It says that whenever you have a partition of a set, you can use that to define an equivalence relation. So let me break this down into part 1. So part 1 is just what I said. So tilde, suppose you already have an equivalence relation on your set, and then you look at the quotient space. That's just a collection of all of your distinct equivalence classes, all of your X bars. Well, that set is a partition of the set. So the quotient space forms a partition of your set. In other words, each of those equivalence classes is not the empty set. If you look at any 2 of them, they're either the same or they're disjoint. And when you union up all of those equivalence classes, you get all of A. And then the second part says, okay, suppose someone gives you a partition of your set A. So I don't have an equivalence relation at this point. I just have a partition. Someone's taken the set and chopped it up into some pieces. Now what we can do is define an equivalence relation. So we define tilde on A. So A is equivalent to B. If there exists one of these sets in the partition, this B alpha, such that A is in B alpha and little b is also in big B alpha. So essentially what A equivalent to B means is that there's some partitioning set that they're both an element of. They're in the same cubicle. Then it turns out that that is an equivalence relation. What this theorem is really telling you on some level is that equivalence relations and partitions, they're really the same thing. If you have a partition, you have an equivalence relation. If you have an equivalence relation, you have a partition. So partitions and equivalence relations are sort of 2 sides of the same coin. All right, so let's see how this works on some particular examples. This is the previous example that we did. We had this partition here of the set 1 through 10. We checked that it was a partition. If we apply part 2 of this theorem, we know that there's an equivalence relation, tilde, defined by A tilde B, if there exists an alpha. I don't really have an indexing set up for this particular example, but I can just say it this way. If A and B lie in the same set in P, so we know this is an equivalence relation, and we know what the equivalence classes are. 1 bar, what are the things that are equivalent to 1 bar under this equivalence relation? Well, our equivalence relation says that 2 elements are equivalent to one another if they lie in the same set in the partition. So 1 bar would be equivalent to, or 1 bar would be the set containing 1 and 4. 2 bar would be the set containing 2, 3, and 5. Then we'd have 6 bar is the singleton 6. 7 bar is 7, 8, and 9. And then 10 bar is the singleton 10. So those are our equivalence classes. The equivalence classes are exactly the sets in the partition. So we started with the partition. That gave rise to an equivalence relation, the equivalence classes of which were exactly the sets of the partition. And then going the other way with that theorem, if we would consider Congruence Mod 3, the example we did in the skills check, remember we formed 3 equivalence classes, 0 bar, 1 bar, and 2 bar. So here's what we know. We know that those equivalence classes, 0 bar, 1 bar, and 2 bar, by part 1 forms a partition of Z. And that's plain to see. 0 bar consists of the multiples of 3, 1 bar consists of the multiples of 3 plus 1, and 2 bar consists of the multiples of 3 plus 2. And when you look at all those numbers, you've got all of the integers. And also those 3 sets, each one of them is not the empty set, and when you look at any 2 of them, they're disjoint from one another. So this is a really cool theorem. And the reason it's cool to me is because it takes 2 concepts which on the surface, they seem completely unrelated. Partitions are just taking a set and chopping it up into some pieces. Equivalence relations have to do with defining how elements can be equivalent to one another in a set. But it turns out that really equivalence classes and partitioning sets are really just the same stuff. So partitions and equivalence relations are really the same thing. That's really cool. So now what I'd like to do is to prove this theorem. There are two parts to the theorem. The part where you start with an equivalence relation and prove that you get a partition, and then the converse, if you start with a partition and define the equivalence relation as stated in the theorem, that is in fact an equivalence relation. Let's see how that goes. This is an important theorem, so I think we should go through the proof of it carefully. So let's make sure we have it in our minds what we're going to prove. So the first part, we're going to start with an equivalence relation and then prove that the quotient space forms a partition. So let tilde be an equivalence relation on the set A, and we're going to consider A mod tilde, which is the set of all x bars where x is an element of A, and we're going to show that that set is a partition. So to show that A mod tilde forms a partition of A, we must establish the three properties of a partition. So first thing we got to establish is that the individual sets in this partition are not the empty set. Notice that A itself is the index set for our partition. So for each x in A, notice that x is an element of x bar, since x is certainly equivalent to itself by reflexivity. So x bar is not the empty set. So each of the sets in our partition are non-empty. That's the first thing we needed to establish, and we're done with that. The second thing we have to establish is that if you take any two equivalence classes, they're either the same equivalence class or they are completely disjoint. Let's let x and y be any two elements of A, and we'll consider x bar and y bar. So there's one of two possibilities. X bar and y bar are disjoint or they're not. If x bar intersect y bar is the empty set, we're done, because we're trying to prove that either x bar and y bar are disjoint or they're equal. So if they're disjoint, we're done. So suppose x bar intersect y bar is not the empty set. So now we're supposing that our two equivalence classes have some overlap. And what we're going to show is that if that's the case, they actually have to be the same. So we're going to argue x bar has to equal y bar, and then that will establish what we need for part B, because for part B, what we got to show is that either x bar intersect y bar equals the empty set or x bar equals y bar. How do we argue two sets are equal? Well, we can do it by double containment, or we can do it by wrangling with the definition of the set. I think I'll do a double containment argument here. So let's do it like this. So let's say little a is in x bar. Then all that means is that a is equivalent to x. Now, by our hypothesis, we're supposing in this that x bar intersect y bar does not equal the empty set. So let's make use of that. Since x bar intersect y bar is not the empty set, there exists some, I don't know, let's call it b in x bar intersect y bar, so that b is an element of x bar and b is an element of y bar. And that just means if b is in x bar, that means that b is equivalent to x, and the fact that b is in y bar means that b is equivalent to y. Okay, so I'm going to try to wrangle some of this stuff together. So we know a is equivalent to x, and we know b is equivalent to x, and then we know b is equivalent to y. What I'm going to argue is that a is equivalent to y, which would mean that a is in y bar, which is what I'm trying to establish. Eventually I'm wanting to show a is in y bar. That's my object, because I started with a in x bar, and then I'm trying to show a is in y bar. So maybe you can see kind of how to stitch that together. If a is equivalent to x, but then x is in turn equivalent to b, then I can use transitivity to get a is equivalent to y. So let's do that. We may have to make use of the symmetry property. So now we have a is equivalent to x, and then we have b is equivalent to x, which implies x is equivalent to b by symmetry. And then we also have b is equivalent to y. So by transitivity, applied twice, a is equivalent to x, x is equivalent to b, so that tells me a is equivalent to b, and then a is equivalent to b and b is equivalent to y, gives me a is equivalent to y. We deduce that a is equivalent to y, and therefore a is an element of y bar by definition. Y bar is the set of all things equivalent to y. So what we've established here, we started with a in x bar and we arrived at a is in y bar. And then doing the reverse containment is similar. I'm just going to leave that to the reader. And then that establishes part B of being a partition, that if you have any two equivalence classes, they're either the same or they're disjoint. And then part C of being a partition is the union of all of the equivalence classes forms the whole set A. Maybe I can do something sneaky and quick here. Okay, so here's a pretty cool trick. A, any set, is the union of all of its elements. So A, all I'm saying here is that A is the union of all the singleton elements in that set. But this, I claim, is a subset of the union over all the x's in A of those x bars, and this is since x is always an element of x bar. So each one of these sets here in this union is a subset of x bar. But then this in turn, I claim, is a subset of A, since we know that each x bar is by definition a subset of A, right? All the things that we were unioning here was a subset of A, so if I union up all those things, I'm still going to have a subset of A. So if you look at what we have here, A on the one hand is a subset of this, but on the other hand, it's a superset of it. So we deduce from this that A is a subset of the union of the x bars, and A contains the union of the x bars. So by that double containment argument right there, we see that A equals the union of the x bars, which is what you need to show. So we've established all three properties of it being a partition, so that's that. So we proved that if you start with an equivalence relation, then the quotient space forms a partition. So now let's look at the proof of part 2. This is where we suppose we've got a partition, and then we define an equivalence relation by saying two elements are equivalent if they're in the same set of the partition, and then we got to argue that that's an equivalence relation. Here we'd have to let some family of sets, B alpha, be a partition of the set A, and we need to define tilde on A by A is equivalent to B if there exists some partition set such that A and B are both in that B alpha. Okay, so now we want to prove that tilde is an equivalence relation. So to prove tilde is an equivalence relation, we establish that tilde is reflexive, symmetric, and transitive. So for reflexivity, we'll take any element of the set A. We know, because we have a partition, we know that A is the union of all those B alphas. And we have little a as an element of big A. So that means little a is in this union. Now, anytime you're in a union, there has to exist some element of the union that you lie in. To be in the union of a family of index sets, by definition, when we define the union, it means that you would have to be in at least one of them. So A is in one of those B alphas. And this is going to seem silly to write, so thus it is certainly true that A is an element of B alpha and A is an element of B alpha. So I'm just writing the same thing twice. But the reason I'm writing it is to see that it matches the definition that A is equivalent to A. So A is equivalent to A because, for A to be equivalent to B, you had to have A and B both in the same set. But here I have A and A are in the same set, so that means A is equivalent to A. So that one seems a little silly, but that's how you'd have to prove it. And then for symmetry, I think symmetry is fairly trivial. For symmetry, we'd have to let A and B be arbitrary elements of A, and suppose A is equivalent to B, then we know what that means. There exists some alpha in the indexing set such that A and B are both in this B alpha. So it's certainly true then B and A in that order are in B alpha. So B is equivalent to A. And then for transitivity, I think that's also fairly trivial. If you take three arbitrary elements and you suppose that A is related to B and B is related to C, then we know there exists some, let's say, alpha and beta in the indexing set such that A and B are in some B alpha and B and C are in some B beta. Well, maybe this is less trivial than I initially thought. We're going to have to take advantage of the fact that two sets in the partition are either equal or disjoint. So notice little b is an element of B alpha and little b is an element of B beta. So that tells me that little b is an element of B alpha intersect B beta. So B alpha intersect B beta does not equal the empty set. So here what we have is two sets in the partition that are not disjoint. And if they're not disjoint, they must be equal according to the definition of partition. So we know B alpha equals B beta. Thus, what we have is A, B, and C are all in B alpha, which is equal to B beta. So in particular, A and C are in B alpha, and that implies that A is equivalent to C because A and C are both in a common set in the partition. And that's the definition of what it means to be equivalent, according to our definition of our equivalence relation. And that's the end of that proof. This is a long proof. It's a lot to digest, but I think if you step through it carefully, you'll see that most of it makes a lot of sense, but it does require that you keep in mind all those different definitions like partition, equivalence relation, equivalence class. So there's a lot going on in terms of definitions, although none of the particular steps that you do are particularly like clever or complicated. So it's just a lot though. So anyway, this is one of those instances when you're watching a video, you can always pause, you can always rewind, and by all means, please do be working actively too. Like, be writing the proof out for yourself. Try to see how much you can do, then listen to the video, sort of interact with the video instead of just listening passively to it, because this gets to be a lot to try to just take in sort of linear time. Dissect it. Make sure that you understand it. Here's another kind of interesting fact about equivalence relations. Anytime that we have a new concept, we kind of want to see how it interacts with our basic set operations. Everything that we're defining is based on sets, and we have these set operations like intersection, union. There's also set difference and set complement. And we can kind of ask ourselves, like, if we have two equivalence relations on the same set A, we could certainly union them together, because they're like, if R1 and R2 here are just equivalence relations on A, that means that they're both subsets of A cross A. So I could certainly union R1 and R2, and I'm going to get another subset of A cross A, which is potentially another equivalence relation on A. So I could union them, I could intersect them, I could take their set difference, and I could start asking about like, when I do that, do I still have an equivalence relation? Part 1 here says that if you intersect two equivalence relations, you get back an equivalence relation. But if you union two equivalence relations, you don't necessarily get back an equivalence relation. You'll get back a relation that has the reflexive and the symmetric properties, but somehow it will fail to have the transitive property. I will prove part 1 of this, and I'm going to leave part 2 as an exercise. So let's do proof of 1. So let R1 and R2 be equivalence relations on A. So that means they both have reflexivity, symmetry, and transitivity. So here we prove R1 intersect R2 is an equivalence relation. So we need to establish reflexivity. So to do that, I'm going to take an arbitrary element in the underlying set A, and I want to show eventually that A is related by the intersection R1 intersect R2 to A. Well, let's see how we can go about that. So now R1 is reflexive. Let me format this a little better here. So R1 is reflexive because it's an equivalence relation. So that tells me that A is related by R1 to A, which another way to think about this is A comma A is in R1. And similarly, R2 is reflexive, which tells me that A is related to A in R2, which tells me that A comma A is in R2. These last two facts taken together tells me that A comma A is in R1 intersect R2, right? Because A comma A is in both of those sets. So it's in the intersection. And then that, just using a different notation, tells me that A is related to A by R1 intersect R2. So if you look at the broad strokes of this proof, I started with an arbitrary element, and then I showed that that element is related to itself by the relation that I'm trying to show is reflexive. Okay, let's do symmetry. So here we have to take two arbitrary elements of the set, and we need to suppose that those two elements are related. So we need to show that A is related to R1, A is related to B in R1 intersect R2. This means that the ordered pair A comma B is in R1 intersect R2, which is the same as saying that A comma B is in R1 and A comma B is in R2. And so R1 is symmetric, and we know A comma B is in R1 tells me that B comma A is in R1. And similarly, R2 being symmetric and knowing that A comma B is in R2 tells me that B comma A is in R2. Now we have B comma A is in R1 intersect R2. Or, using the other notation, B is related to A in R1 intersect R2 in that order. So broad strokes, we started with A was related to B in that relation, and we got to B is related to A in that relation. And so that establishes symmetry. And then I'll start transitivity on the next page here. For transitivity, we would let A, B, and C be elements of A. And we got to suppose that A is related to B in the intersection relation, and B is related to C in the intersection relation. Okay, so this says that A comma B is in R1 intersect R2, and B comma C is in R1 intersect R2. So this says A comma B is in R1, and A comma B is in R2, and B comma C is in R1, and B comma C is in R2. Well, this is the same as saying A is related by R1 to B, and A is related to B by R2, and B is related by R1 to C, and B is related to C by R2. And I just want you to kind of focus on these two things in pairs like this. Here, this focuses on R1, right? Which I know is transitive. So if A is related to B and then B is related to C in R1, then I'm going to get A is related to C in R1. And then similarly over here, I have R2 is transitive. And so I'm going to have A is related to C in R2. And then from there, I get the intersection bit. So this is how we're proceeding. So now, since R1 and R2 are transitive, A is related by R1 to C, and A is related by R2 to C. So that tells me that A comma C is in R1 and A comma C is in R2. That tells me that A comma C is in the intersection. And for the grand finale, that tells me that A is related to C in the intersection relation. And then I'm going to look again at the broad strokes of what we did here. We started by taking the hypothesis that A is related to B in the intersection relation, and in turn B is related to C in the intersection relation. And then we arrived that A was related to C in the intersection relation. And that's transitivity. One thing is an interesting feature of this proof is how we're going back and forth between ordered pair notation and relation notation. The ordered pair notation is nice whenever you want to think about sets and you're doing set operations. So I want to see that is an element of sort of thing, so that I can say, well, if this element is an element of this set and it's also an element of this set, then it's in the intersection. So sometimes you switch notation as a matter of convenience, depending on what you're trying to prove. If I'm trying to prove something about set operations, I want to see something about elements of. Other times, it may not be necessary, so taking advantage of the notation can really help out your proof. Okay, I think I'll go ahead and stop this lecture here. This is a pretty big lecture. There were a lot of concepts here. So I wouldn't expect that you just watched this video through in one setting and totally absorbed all of it. We started with relations, and relations, that concept itself is not a super challenging idea. A relation is simply a collection of ordered pairs inside of a cross product. In other words, it's a subset of a cross product. But associated with relations, we started talking about domains, ranges, images, preimages, and those definitions are a little technical because they involve quantification, and sometimes it takes a little bit of time to wrap your mind around those definitions, and you need to digest as many examples as you can. And I gave you several examples, and in exercises that you do for homework, you'll do more of that sort of thing, and hopefully you'll get those ideas implanted in your mind. But then we started doing proofs of facts involving those concepts: domain, range, preimage, image, and we will continue to use those concepts as we move forward. So it's really critical to go back and take your time with this video, press pause as you need to, especially on the proofier things, the more abstract parts, and make sure that you're digesting it. Write down any questions that you have. Make notes of things that are confusing, and be sure that that gets addressed before you really move on, because it will catch up to you. We will continue to work with images and preimages when we go to talk about functions, domains and ranges for sure. And then next we did equivalence relations. And associated with equivalence relations, we have these three properties: reflexivity, symmetry, and transitivity. And so we had some good templates for proofs of those types of things here in this lecture. And so that's something you really need to get mastery of. And we also talked about equivalence classes and quotient spaces, which are an important concept. I've noticed that sometimes students have a little trouble with getting their heads around this idea of equivalence classes. Start with the basic examples and work your way up. And then we started doing proofs of things involving equivalence classes and quotient spaces and partitions. And here at the end here, we had a pretty long proof or two. And these again are things that you're going to have to slow down, press pause a lot, make notes, address those things that confuse you before you really move on. Equivalence classes are super big, important in all branches of higher mathematics. So this is something you really need to come to terms with, especially the idea of a quotient space. I remember being confused about quotient spaces because it's a level of abstraction. You're taking a set, A, and then you're forming a new set on top of that, which is kind of related, kind of the same, but kind of has some of the properties of the original set, but it's sort of a distillation of it. And that takes some time to get some mastery of there. And anyway, hopefully by carefully parsing through these videos and also doing exercises on your own, things will start to cement in your mind. But just remember, this is a process. When you see these new concepts for the first time, it's natural for them to seem kind of vague and intimidating, and might seem impossible to get your mind around, but you'll get there just by sticking with it. And I usually find that it's helpful to have really good basic examples that you can relate back to as sort of an exemplar of this concept. So for me, when I'm thinking about quotient spaces and equivalence classes, I always think about congruence modulo n. It's kind of like the example for me that really exemplifies what an equivalence relation is about, and also working with proofs of it. Really, those proofs are typical of how you prove things about equivalence relations in general. So Congruence Mod n is a good one to really spend some time with. Okay, I'll stop there. Talk to you again soon. Bye.